mass and multi-body orbits. Purpose of this lab is to determine the mass of a black hole using motion of an orbiting star and simulate a spaceship orbit influenced by both moon and planet. And the main result is the estimated black hole has a mass of 1.32 times 10 to the 34th kilograms. Physics principles, Newton's second law, net force on an object equals the rate of the change of momentum. And the momentum is P equals mv. Gravitational force is F equals G capital M lowercase m divided by r squared, with all of these being the different meanings of those variables. And then assumptions, the only force acting on the star is gravity from the black hole, and only gravity from the planet and the moon act on the spaceship. Systems and initial conditions. The system for part 1 is a star orbiting the black hole located at the origin, and for part 2, the system is the planet located at the origin, moon orbiting the planet, and spaceship launched from the moon. For the surroundings for both of them are empty space, no air resistance, and only the gravitational forces. Initial conditions, star has a mass of 2 times 10 to the 30th kilograms, and time step is 1 Earth day, which is 24 hours times 60 minutes times 60 seconds. Spaceship starts at 100 meters above the surface of the moon, and the initial velocity is chosen experimentally. The computational model of part 1 is, these are the screenshots of the code. The program analyzes orbital motion using the following steps. It imports star position data and then calculates velocity from position changes. It then calculates momentum using P equals mv, and then calculates its change of momentum, which is change in p over change in t. Uses Newton's second law to determine the net force, uses gravitational equation to solve for black hole mass, and then the calculation used is at the bottom. And then at the end, it prints out the average mass of the black hole. For part 2, this were the screenshots of the code that was built. Force of the spaceship, F net equals F moon plus F planet. Update positions using new position equals old position times velocity, plus velocity times time. And updates velocity with the equation new velocity equals old velocity plus the force times the mass times time. The results of part 1, individual black hole masses vary slightly due to numerical approximations. They vary from 1.29 to 1.36 times 10 to the 34 kilograms. The average mass was stated earlier, and it was calculated by averaging all mass values from data points, which was done through the code. For the results for part 2, spaceship launched with an initial velocity to orbit both moon and planet. Orbit is complex, influenced by both bodies. It does not crash into the moon or the planet and demonstrates gravity-driven multi-body motion. The orbit, it does not complete due to the code not having enough time to complete it, but it was on its way to being complete. What does it mean? Net force causes motion changes both in speed and direction. Parallel component of force changes speed. Perpendicular component changes direction. And orbital motion, mostly perpendicular forces changing direction, not speed. What if modeling entire system would require all gravitational interactions, which is black hole and star and planet, planet, moon, spaceship, and planet, spaceship. The dominant interactions are black hole and star, planet, moon, and moon, spaceship. And body simulation is needed for accurate prediction. Sources of error, numerical approximation when calculating velocity, finite time steps with 1-day intervals, rounding errors in calculations, assuming only one force in part 1, and ignoring relativistic effects near black holes. In conclusion, it successfully estimated the black hole mass using star orbit. It simulated spaceship orbit around moon and planet. It demonstrated how gravity governs multi-body motion, and computational models validate Newtonian mechanics in orbiting systems. Thank you.